Howdy, this is Mr. Potter. Welcome to day 2 of our discussion of limits dealing with infinity. Today we're going to be talking about dominant functions and also about in-behavior models. So let's go ahead and get started. So the first thing I want to do is I want to talk about the way that we dealt with limits of rational functions from a pre-calculus standard. In our pre-calculus classes, we use such imprecise terms as top-heavy or bottom-heavy. Or neither. And these are situations where I would discuss something like 3x squared plus 4x to the fourth over 2x cubed. I'd call it top-heavy because the dominant term in my numerator was a larger degree than the dominant term in my denominator. And we would say that this would go to infinity. Whereas if I had something that was bottom-heavy, like 3x squared plus 4x to the fourth over 2x to the fifth, if the dominant term in the denominator was larger than the dominant term in the numerator, we said that went towards 0 as x increased without bound. And if we had neither, a situation like 3x squared plus 4x to the fourth over 2x to the fourth, if these ended up being the same degree, what I would do is I would take a ratio of the coefficients and say that my limit tended towards 2 as x went towards infinity. And in both of these situations, these were the situations that we talked about whether or not we had our horizontal asymptote. But we described that in the previous episode about when we have a horizontal asymptote. What we want to do in these situations is we want to deal with this from an algebraic standpoint. In other words, distributing through by some polynomial to reduce the degree, so then I can evaluate an actual limit using the behavior of the parent functions that we talked about in the previous lesson. So let's talk about this situation that we would call top-heavy. In other words, I want to look at the limit as x approaches infinity of 3x squared plus 4x to the fourth over 2x cubed. And I'm always going to want to look at this dominant term in my denominator. I'm going to end up dividing by the dominant term in the denominator. So I'm going to multiply the numerator and denominator by 1 over x cubed. And when I distribute that across the numerator, I'm going to end up with 3 over x plus 4x. And my denominator ends up just being a 2. But I'm still trying to evaluate a limit. A limit as x approaches infinity. And so when I look at it from this standpoint, I know that 3 over x behaves like my parent function, which goes to 0. And I know that 4x behaves like my parent function. This actually goes to infinity. And so what happens is I can say that this limit ends up increasing without bound. And so I don't have a horizontal asymptote as x approaches positive infinity. And in that same token, if I approach x approaches negative infinity, this same ratio ends up going to negative infinity. It ends up decreasing without bound. And so the situation that we used to call top-heavy, I can actually show algebraically that the limit approaches a positive infinity or negative infinity. So I end up with a situation with no horizontal asymptotes. If I end up with a situation where the degrees are the same, and I try that exact same idea by looking at the limit as x approaches infinity of this function, I'm going to multiply the top and bottom by 1 over x to the 4th. And that ends up getting rid of the degree in the denominator, but it also eliminates all the degrees in the numerator. So I just end up with 3 over x squared plus a constant 4 over a constant 2 as x increases without bound. And I know the parent function of 1 over x squared tells me that this goes to 0 as x goes towards infinity. And so I have a ratio of 2 constants, so this limit ends up being 2. And so I can say that I have a horizontal asymptote at y equals 2. And because these don't have any x's, I can consider the limit as x approaches negative infinity to be the same. So that takes care of our top-heavy situation and also the situation where they're neutral. So if I want to look at the bottom-heavy situation, so if I want to take a look at the limit as x approaches infinity of this function, 3x squared plus 4x to the 4th over 2x to the 5th. Now I'm going to me multiplying my numerator and my denominator by 1 over x to the fifth, and that completely eliminates any dominant terms in the numerator. This ends up being 3 over x cubed plus 4 over x, all divided by 2, as x increases without bound. And looking at this term goes to 0 by the parent function behavior, as does this. So I have a constant of 0 over 2, which is 0. And so this is the situation where we'd have a horizontal asymptote at y equals 0. So this is our bottom-heavy case. But we really need to take a look at this from a limit situation. We need to take a look at this from an algebraic. So we're not just using clever phrases or noticing patterns, but instead we're using algebra to show where the limit goes. So I do want to make this real quick note. We've dealt with two different types of situations where we've kind of distributed through to eliminate a term. The thing is, if I'm looking for limits as x approaches 0, then what I want to do is I want to divide by the smallest term. And that's one of those situations where if I'm looking at the limit as x approaches 0 of 3x squared minus 4x to the fourth, let's make it a plus, over 2x cubed plus 7x. I want to look at the smallest term. I want to multiply the top and bottom by 1 over x. And the reason that I'm doing this is because I do want x terms. I just want a constant term left over. I don't want to deal with x's in the denominator. So I'm always going to divide by the smallest term's degree. Whereas if I'm looking for limits as x approaches a positive or negative infinity, then I always want to divide by the largest term. So in this case, if I was looking for the limit as x approaches infinity of 3x squared plus 4x to the fourth over 2x cubed plus 7x. My largest term in the denominator is x cubed, so I'm going to be dividing by x cubed in the numerator and denominator. And of course, that's because 1 over x goes to 0, 1 over x squared goes to 0, and so forth, as x increases without bound. Over here, as x was approaching 0, these polynomial terms go to 0, leaving the constant terms to give me an actual substantive value. So it's just something to note about how I deal with these situations. It's a similar process, but in order to decide which term I'm going to be using, I need to take care of, am I going towards 0 or am I going towards an extreme? So that takes care of our top heavy and bottom heavy discussion. So the last thing I want to talk about today are in behavior models. So I want to talk about how does a polynomial or rational function of two polynomials behave? Because if I were to look at something like y equals 3x squared plus 6x, this does have roots at 0 and at 2. But if I'm looking at the end behavior, this function will actually behave a lot like a regular parabola. That these lines will actually come very close to each other as x approaches 1,000 or 10,000. This actual 6x doesn't mean that much in the grand scale of things as x goes to infinity. So the question is, do I have a linear behavior or a quadratic behavior or a cubic behavior as x increases without bounds? So this is my idea for the in behavior function. And so what we notice is that in general, a function will behave as a ratio of dominant terms. In the numerator and denominator. And that's not a problem if I'm dealing with something that's strictly polynomial, because it's really easy to see what my dominant term is in the numerator, and my denominator ends up being constant. What's more interesting is how do I deal with some situations where I'm dealing with what's really more interesting is how I deal with situations where I'm looking at a ratio of two functions. So let's go ahead and talk about that. Let's say I've got y equals 2x cubed plus 5x squared over 4 minus 4x cubed. So I'm looking at this. My dominant term in the numerator is the 2x cubed. My dominant term in the denominator is the negative 4x cubed. And so I would say that this behaves like this function, which is really just a constant negative 1/2 as x tends towards positive or negative infinity. And looking at this is okay, but I want to explain where this comes from. So what I'm really doing is I'm really looking for the limit as x approaches infinity of this rational function. And the behavior that we just talked about says that we're going to divide out the dominant term in my denominator, which is 1 over x cubed and 1 over x cubed. And so this ends up being 2 plus 5 over x over 4 over x cubed minus 4. And as x goes towards infinity, this term and this term both tend towards 0. So I still end up with that same 2 over negative 4 or negative 1/2 that we noticed. And so what that means is that we have a horizontal asymptote at y equals negative 1/2. And so that's what I'm referring to with this important note about horizontal asymptotes. These horizontal asymptotes, they occur when the degree of the denominator is greater than or equal to the degree of the numerator. In other words, what we learned back in pre-cal as our bottom-heavy situations or our equal situations. So there is one more function that I want to talk about, and that's this function here, where if I look at f of x equals x plus e to the negative x as x approaches infinity, or as x approaches negative infinity. And so what I want to look at first is if I look at this from a graph standpoint, I'll actually notice two things. One is as x approaches infinity, this term tends to be very, very small, almost 0. And so this really is my dominant term. So for values over here, I notice that this starts approaching a linear curve. Whereas if I look at values approaching x equals negative infinity, this is negative, but this ends up being a very, very large exponential. And so this function actually behaves very much like an exponential for negative values of x. And so what I can do is I can look at this in behavior function. I can say, hey, let's take a look at the limit as x approaches infinity, and I want to know, am I really dealing with something that looks like x? In other words, does this end up being a constant value? And so if I look at this limit, I'm really dealing with the limit as x approaches infinity of x over x plus e to the negative x over x. And as x goes to infinity, this is going to 1. As x goes to infinity, this is very, very close to 0. And this certainly goes to 0 much faster than this goes to infinity. So this ends up being 0. So I end up with a constant of 1. And when I end up with a constant, that means that these functions are growing at the same rate. So that means this x plus e to the negative x is growing at the same rate as x is. In other words, x is a good end behavior model for the right side of this function. As I look as x goes towards negative infinity, I'm looking at x plus e to the negative x over e to the negative x. And as I separate my fractions, I end up noticing that I have x e to the x plus 1, as this term cancels out, but here this becomes a dominant term up here. And so this exponential is 0 as x goes towards negative infinity, because this exponential is going towards the left. So this is actually 0 plus 1, which is 1. So I do notice that e to the negative x is my left end behavior model for this function. And of course, when I'm looking at end behavior models, if I wanted to know if a particular function models the behavior well, I'm looking for a constant when I look at this ratio. Ideally, a constant of 1, because that means that I've nailed it. But even if I'm just off by a constant, like if I got a answer of 1/2, or I got an answer of 3, I'm still demonstrating the rate of growth of this function. And rate of growth is something that we'll talk about much more in chapter 3. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.